Hello everyone, welcome to a new video. In this one, we will discuss some practical considerations before starting doing actual simulations. Today, we would like to discuss three important concepts. Uh, uh, Concept number one is fractional versus Cartesian coordinates. So the coordinate system that we will be using in our simulations. The second point that we would like to describe uh, briefly today is periodic boundary conditions, periodic boundary conditions. And finally, the third point that we would like to discuss is energy minimization. And with that, we will, after this, we will start doing actual calculations to showcase some of the concepts that we have illustrated over the previous videos. So let's start with number one, the coordinates. So we'd like to start with the coordinates. We will describe this in two dimensions, although the discussion itself applies to three dimensions. And even more, we will discuss here in a simplified fashion um, um, rectangular case, although a generalization to more general systems like monoclinic or triclinic in three dimensions can be done. And in fact, we will show it in another extra video. So let's start with some simple coordinate system like this, x, y. And suppose we have a rectangle that represents our simulation cell. Again, this is in two dimensions. Suppose, for the sake of argument, that this length, let's call it Lx, equals, 20 angstrom. And this length, Ly, could be something else, maybe 15 angstrom, right? And suppose we do have an atom here in this location, okay? Now, there are two ways to describe the position of this atom. One is the natural Cartesian that we have learned in high school mathematics, let's say, analytic geometry. Suppose that this distance is, 4 angstrom. Maybe this distance is 3 angstrom. And then let's say that this atom is, maybe carbon. It's atom number one. So I would say that atom carbon has coordinates 4, comma 3. So that's a legitimate Cartesian coordinate system. So this is Cartesian. However, you do have another option, which is the fractional coordinate system. You'd say, look, I will take the 4 and divide it by the length of the simulation box along the x-axis. So this is going to be 20. And similarly, the 3 divided by the length along the y-axis, that's 15. And when you do this, you will get 0.2, and this is how much? 1 over 5. This actually happens to be also 0.2, right? So this is 0.2 and 0.2. So this is the coordinate system in fractional coordinates. Now, most of the software packages give you the two options to present the positions of the atoms using Cartesian coordinates or fractional coordinates. And with time, one will get the feeling or the impression when using one or the other would be more useful. So generally speaking, fractional is the best. That's the general thing. However, in certain cases, for example, modeling surfaces of materials, it's actually much more convenient to use the Cartesian coordinates. And during the upcoming exercises, we will discuss this point further to give you the impression why Cartesian could be useful in certain cases. However, as I said, most of the time, the default is just fractional coordinates. Now, as I described at the beginning, while this was discussed in a two-dimensional fashion, it's easy to generalize to three dimensions where you have a z coordinate. And it's also possible to generalize it for non-rectangular symmetries, something like triclinic or monoclinic. So that uh, is the fractional versus Cartesian coordinates. Now, the periodic boundary conditions. Let's move to another page here. So number 2, periodic boundary conditions. Whenever you run a mathematical simulation, you really need to describe the boundary conditions. And depending on your field of study, you might have different kinds of periodic boundary condition of conditions of boundary conditions. For example, when you solve differential equations, boundary value problems, you have to specify these. For us in computer simulation of materials, we usually use the periodic boundary conditions. And there is one overarching goal for this. The main purpose for this is to simulate bulk and avoid surface effects. So, for example, let's say someone asked you to study gold or to study copper or to study iron oxide, right? Any one of these materials. Most of the time, you are interested in the thermodynamic limit, in the limit where you have a bulk, a big chunk of this matter, something on the order of, maybe few centimeters, something you can see with your eyes. But then if you count how many atoms are there, this is a huge number of atoms, and it becomes computationally demanding to run a simulation for such a number of atoms. Instead, what you can afford is running maybe 200, 300, maybe 1,000, a couple of thousands, maybe million atoms. But million, even if you take a million atom, this is a very small number, this is really, really small element of the material. This is something like on the order of 10 nanometers by 10 nanometers by 10 nanometers, right? So even though it's a million number of atoms, it's still small and actually microscopic in the sense of, can you see it with your eyes or not? But then, and even worse, that this 10 by 10 by 10 nanometer has a lot of surfaces, and these surfaces would affect whatever property you want to calculate. Instead, what what you would love to have is something on the order, few centimeters here, few centimeters there, and so on. But you cannot achieve this on your computer. So one way to achieve it is periodic boundary conditions, which in a sense allows you to simulate infinite number of atoms, bulk. So to illustrate this, again, let's appeal to our two-dimensional picture. Suppose this is our simulation box. You have maybe a pink atom here, maybe a yellow atom here, and anything, a green atom here. Again, if you leave it like this will be only 3 atoms, and it's not a complete picture. Now, what your software automatically does for you is applying periodic boundary conditions in X and Y. That's to say, it extends this in an infinite number of images. In fact, they are infinite number of images. I'm only showing here one on the left and one on the right, but really, really, there are infinite number of them. And the same story goes along the y-axis, right? And even more in linear combinations of x and y. So you also have an image here and an image here and an image here and an image here. So your original box has been duplicated an infinite number of times, right? In x and y. Actually, the same story goes in the z direction. If you have the z direction three-dimensional system, then the duplication also goes along the z-axis. Now, you do have an image of each one of these atoms in these boxes. And in fact, in terms of interactions, especially something like column interaction, you do actually calculate the interactions with these images, right? You do calculate the interaction with these images. So in a sense, you are simulating an infinite number of atoms. However, this infinite number of atoms is repeated, right? It's duplicated inside. And that's, what which will lead us to some at some point in some exercises we will illustrate this, is sometimes your original box is not big enough. You might tell me, why do I care about the size of the box? Why I should make it larger? I'm using periodic boundary conditions, then in principle I'm doing infinite number of atoms. But in certain cases, especially when you study something like a defect or something that breaks symmetry in general, then you might need to make your cell bigger. We will illustrate this in more details in a practical exercise. But for now, all what matters to us is that your original cell is duplicated infinitely in all directions, and even linear combinations of these directions. Now, this has some funny implication, especially we will see this when we study molecular dynamics. The funny implication is the following. Suppose, for example, this atom here um, during molecular dynamics simulation actually moves to the left. Then, in fact, this image will move to the left, this image moves to the left, this image moves to the left. But in particular, this image will move to the left and enter the original simulation box. So that means the pink atom left the box from the left side, and at the same instant, its image enters from the right side. You see, the same story goes to any atom. For example, this one can move up, exit the box from here, and then its image from below will actually also move up and enter the box. So this is one of the funny implications of the periodicity. Periodicity, it's as the name implies, the thing is repeated periodically, and that's why when one atom moves, another image enters in, right? Again, we will make a special video, an extra, I would say it's an sort of extra credit, if you wish to call it this way, to elaborate more on the implications of this periodicity, especially for non-cubic systems where things can becomes a little bit more complicated mathematically. How do you handle them? Okay, but that's it. That's the concept of periodic boundary conditions. And finally, the last practical consideration we would like to discuss um, before we actually take some exercises is energy minimization. Energy minimization. What usually happens is that you get some initial guess for your structure. The initial guess could be coming from experiment, for example, or from any other source, maybe another simulation technique, let's say. For example, you are studying, BCC iron, and you have some initial guess. I'm just giving numbers here. Don't quote me on these numbers. Maybe the unit cell length is, let's say, 2.7 angstrom, and it's body-centered cubic. That's to say, there are atoms on each corner, and then there is an atom in the center of the cube. And these are only considered as initial guesses. Where do you get this initial guess? You would get this, as I said, either from an experimental measurement, from online database. You can even these days ask one of the AI tools to give you some initial guess for any material that you would like to study, right? But then you would like to make sure using your energy model, let's say Leonard-Jones or Buckingham or embedded atom method, any one of the uh, energy models that we have discussed over the last videos, you want to make sure that you minimize the energy, that you actually reach to the minimum energy structure. And usually to do this, you need first to calculate the energy. So to do energy minimization, the first step, you need to compute the total energy of the system. Remember, there are no motion here. This is, in a sense, this is 0 Kelvin in terms of temperature. This is 0 Kelvin calculation, and there is no kinetic energy. It's purely potential energy, right? When we do molecular dynamics, you will start getting some kinetic energy representing the temperature of the system. But as of now, in this chapter of the course, we are only having potential energy. So you see, and again, there is some subtle detail here which we can discuss in one of our exercises. But if you have some basic knowledge in crystallography and material science, you would know that in this crystal structure, this unit cell actually contains two atoms, which are these guys, right? The other ones are, shared, but this is another story. Let's leave it so that we don't interrupt our discussion. All what you need to calculate uh, is the total energy of the crystal, right? And then usually the second step is to calculate the forces on each atom. The energies you will use whatever. You will use Lennard-Jones, you will use embedded atom method, Buckingham, any technique. And then the force, you want to know the force on this atom and the force on this atom. And if you have other atoms in the cell, you also would like to calculate the forces. And from the theory of mechanics, we know that the force is negative the gradient of energy. So uh, um, you can actually calculate uh, um, uh, by differentiating the energy with respect to position, you can calculate the force vector on each one of these atoms. And then you use one of the algorithms to minimize the energy. Any algorithm that's studied in the theory of optimization, something like conjugate gradient, depending on your software, you usually don't write a code for that. This is already implemented in your software. Something like the conjugate gradient algorithm, something like Newton-Raphson algorithm. There are other algorithms as well that can do energy minimization. And these algorithms will suggest a way to minimize the energy. Sometimes this suggestion is by simply moving atoms, right? Maybe it suggests that this atom is exercising or is affected by some force in this direction. So maybe if I move it up a little bit, this force will be minimized, or this atom needs to move downward. Of course, in perfect BCC symmetry, this doesn't happen, right? But in a more general case, yes, it might suggest that you need to move some atoms. Or it can suggest something even more dramatic than this to minimize the energy, and that's actually to shrink or expand the size of the cell. So instead of 2.7, your software or your numerical algorithm can suggest, no, 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 not 2.7, let's make it 2.65 angstrom. And usually this process is iterative. You go back again. This is like a loop, right? Um, you keep going through this loop, calculating the energy, forces, conjugate gradient, and then you repeat until you reach to some stopping criterion. You need some stopping criterion to stop this energy minimization. For example, when the energy at iteration number n minus the energy at iteration number n minus 1 in an absolute sense is less than maybe, 10 to the power negative 6 electron volt, then you stop your iterations. Every software and every numerical technique has its own intricate details about how you decide the stopping criterion, and we will discuss some of these ideas in the exercises. But this is the general idea, is that you calculate energy and then forces, you apply a numerical algorithm which can suggest that you need to move one of the atoms up or down or left or right or any direction, up, front and backwards. It might also suggest that you need to change the cell size. And then the conclusion is that after you do this technique repetitively and satisfies the stopping criterion, you reach to what is known as the minimum energy structure. You need to reach to something called the minimum energy structure at the end. One last word before we conclude this video on this. And this is a concept that's very deep and very fundamental in the theory of materials. You can, and we will actually try to discuss it in later chapters as well. You can imagine a landscape for energy versus some general coordinates. When I say general coordinates, I don't mean X, Y, Z, and it's really generalized coordinates that could contain X, Y, Z for all atoms. And maybe if you are discussing a dynamic situation, it could include the velocities of each one of the atoms in the system. I'm drawing this in one dimension, but it's a multi-dimensional landscape. But just to simplify the idea, you could have something that looks like this. And of course, there could be other details, but this is enough for the quick discussion we are doing now, where you have uh, a global minimum. For example, if you are studying simple crystals or simple metals, this could be, for example, FCC, face center cubic. You might have a local minimum here. This could represent a hexagonal close-packed crystal. And you might have another local minimum or several local minima. So this is another local minimum here. This could, for example, represent PCC crystal structure. I just want to illustrate one concept here because we will get to this graph again and again in this course trying to understand some deeper concept about the theory of materials. Suppose you start your simulation, let's say here. This is your initial guess obtained from experiments, let's say. Just go to the previous slide. This is, for example, the initial guess you got from experiments. What your algorithm, conjugate gradient or Newton-Raphson, is trying to do is systematically minimizing the energy. You see, I'm going down the energy axis, hoping to reach eventually to this local minimum. What you should know at this stage very well is that your conjugate gradient or Newton-Raphson or any one of these optimization algorithms will not allow you to take the leap of jumping from one of the basins to another basin in the energy landscape where you go to the global minimum. It will not allow you to do this. There are other techniques to do this. For example, Monte Carlo, which we will study in a later chapter. But for now, our best hope is that we start from some initial guess and we systematically go downward to reach the local minimum in this energy base. Okay, so let's summarize now what we discussed today. Today we discussed three concepts: fractional coordinates, periodic boundary conditions, and energy minimization. For coordinates, you can use the natural Cartesian, but usually the preference is to use the fractional, where you take the Cartesian and divide it by the length of the box. Periodic boundary conditions are useful to allow you to simulate bulk and avoid surface effects. And in a sense, you are really simulating an infinite number of atoms because you have infinite number of images. There are some subtle details related to periodic boundary conditions. We clarified some of them today. For example, when you see an atom leaving the box from the left, another one will enter from the right to maintain the net number of atoms inside the box consistently the same throughout the simulation. And finally, we discussed the concept of energy minimization, which will be the key exercise we will do in our practical calculations. Usually you start with calculating the total energy of your system, forces on each atom, apply a numerical algorithm that allows you to minimize the energy. This could be by moving one of the atoms, one or several atoms, and it could also change the volume or the lattice parameter of your simulation cell. And then you will keep repeating this until you satisfy some stopping criterion and reach to the minimum energy structure. How this looks like in an energy landscape, what's happening is that you start from initial guess and you try to reach to the local minimum in the energy basin that you started in. Thank you so much and see you later in one of the practical calculations.